2.8 is titled Complex Fractions. Complex does not necessarily mean complicated, because lots of fractions are complicated but wouldn't fall into this category. Complex fractions specifically are fractions inside of fractions. So if you'll recall, division is the same as multiplying by the reciprocal, right? So when we write down something that says divided by 3, we recognize that that's equivalent to multiplying by 1/3. Do you remember doing that? Okay, fabulous. So that's the crux of working in this section, is remembering and recognizing that reality about the relationship between multiplication and division. So we're going to do lots of examples. They'll start out pretty straightforward, and they'll get more complicated as we go. The first one that we see is actually a division by 3, much like the example that I just referenced. This says 5/3 divided by 3. So this is the same as 5/3 times 1/3, right? So this is dividing by 3, and I'm changing it to being multiplying by 1/3. Once it's in that form, we're going to use all the things that we know about multiplication of fractions, and we'll either simplify first if we can along diagonals or so forth. And then when we're done with that, or if we choose to do it at the end, we're multiplying across the top. So this would be 5. Multiplying across the bottom, this would be 9. And if there's any reducing, we would reduce. This one doesn't have any, so we would be done. Now, I kind of like to justify why this works again, or to remind you. Imagine that you had 5/3 of a pizza. So that would mean you had one whole pizza and a 2/3 pizza, right? And if you're dividing it by 3, what you're asking is to split it into 3 equal pieces, right? Well, that's the same thing as 1/3 of the pizzas that you started with. So that's why that's happening in that relationship there. Number 2 actually has a fraction on top and a fraction on bottom, right? But it's not any more difficult than the one that we just did. We have the fraction on top, it's 3/5. And then when we divide by 9/14, it's the same thing as multiplying by the reciprocal, 14/9. So we flip the bottom. It's always the reciprocal of the bottom. So we've got 14/9. Now on this one, it actually has the ability to be simplified before we do the multiplication. You don't have to do it in that order, but it's kind of nice because we're working with smaller numbers. So I would be inclined to notice that the 3 and the 9 would reduce. So they both divide by 3. 3 divided by 3 is 1, and 9 divided by 3 is 3. So that my multiplication is a little bit smaller to deal with. 1 times 14 on top is 14. And then 5 times 3 on bottom is 15. And I get 14/15, which doesn't reduce. If you happen not to notice, or just don't usually think about simplifying along diagonals first, that'll be fine. What will happen here instead is you'd actually have to multiply the 14 times 3. I don't know what that is. Does anybody else know? Is it? Yeah, it's 42. You'd get 42. And then you'd multiply the 5 times 9, which is 45. But at this point, you'd have to remember to reduce, because you're very likely, once you deal with the larger numbers, to get things that would reduce. This one does. They both divide by 3. So at some point, you're going to divide by 3, whether you're doing it at the initial setup before you do the multiplication, or whether you do it at the end after you've gotten your result. So no matter what, your answer will still end up as 14/15. Okay? Your choice. 3 is messier. What is it about 3 that makes it messier? Yeah, there's some addition and subtraction within those numerator and denominator, right? So this whole idea of multiplying by the reciprocal of the denominator worked just fine when the denominator is a single fraction. But this denominator on 3 and on 4, because it's on my same screen, you don't have a denominator that's a single fraction here. Agreed? Yeah, so it's not so friendly to just say, oh, I'm just going to multiply by the reciprocal, because I don't even have a single fraction in the bottom to be talking about that way. So there's actually a much nicer way to handle this. We've seen something like this before, but you might not think of using it right now. We saw this when we were solving equations, and we said, you know what, I don't really like all the fractions involved in the equations. Could I just somehow eliminate the extra fractions that are going on? And we did that by deciding, sure I could, I just need the least common denominator. So if I take a look at the little denominators here, I have a 5 and I have a 4. You guys see that? 5 and 4 don't have anything in common, which means that the least common denominator of the 5 and 4, I'll just remind you what the denominators are we're working with, the 5 and the 4, would be 20. It's just the two of them multiplied. So check this out. I can multiply the numerator by 20, and I can multiply the denominator by 20. Now I want to be a little bit careful because sometimes people forget that this multiplies both pieces. So I'll take a step here to write out maybe a little bit more than you might wish I were writing, or maybe a little bit more than you might need to write as you get comfortable with these. But what we're really doing is 1 times 20 minus 7/5 times 20, right? We're multiplying both pieces of the numerator by 20. And same thing on the denominator. I need to multiply both pieces of the denominator also by 20. So I have 7/4 times 20. And I have plus 2 times 20. Okay, so why did we do that? Well, we did that because those fractions that we had, right, that 7 over 5, this is 20 over 1, right? That's what it means to multiply by 20. So when I reduce this as 5 and 20, 20 divides by 5 and it gives me a 4. So I don't have that little denominator of 5 anymore. And the same thing happens in the denominator. This, oops, I left my 0 out of my 20 here. So sorry. This 4 and this 20, they also reduce because 20 divided by 4 is 5. So there's no little 4 denominator either anymore. So I can do all the multiplications that are present. 1 times 20 is 20. Then I have minus 7 times 4 would be 28, so minus 28 over, now I have 7, whoops, sorry about that, 7 times 5, which is 35, and then there's a positive, a plus sign, and the last piece is 2 times 20, so I have 40. There are no denominators, little denominators left. You no longer have a fraction inside of a fraction. And each of those pieces is fairly straightforward to do the subtraction or the addition with. So 20 minus 28 is negative 8. 35 plus 40 is 75. And then we would ask ourselves if 8 and 75 have anything in common. They don't. 8 only divides by numbers that have 2's in them, like 2 and 4, and 75 won't do that because it's odd. So we're done at that point. But eliminating the fractions is the simplest way to do that kind of a problem. I don't want fractions inside of our fractions. It makes it very difficult to work with. So if I follow that same reasoning for my next problem, I have 4 little denominators, a 5, a 2, a 2, and a 4, and I need the least common denominator of all of that. Now, a common denominator of all of that would be simply to multiply them, 5 times 2 times 4. I could do that. It might be more than I need, but it would certainly work. So if you struggle to figure out, well, what's the smallest number, you could always just use a number, a denominator number, right? Multiply all the denominators together, be good to go. Now, we could also find the least common denominator. So the 3 little denominators are 5, 2, and 4, right? But what you might notice is that 2 and 4 already share a 2 in common as a factor, right? So I don't really need the additional 2 that's here to consider. If I multiplied 5 times 4, I'd get 20, like on the last problem. And it would take care of the 2 as well. It just happens to work on this one. So if I multiply, or if I find my least common denominator here, it's also 20. They're not always 20, I promise. It just worked out that way on those 2 problems. If you didn't recognize that and you multiplied 5 times 2 times 4 and got 40, it'd be okay. Your numbers will be a little bit bigger to work with, but they won't be unreasonable. You'll still be able to work with them. So now we're going to multiply by 20 on the top and the bottom. So I'm going to go ahead and take the time to write them out just like I did in the last one. I'm going to leave it up to you whether or not you feel you need to see that written out. If you feel like you can go from here to the last step with the simplification, that's okay. But I know sometimes it's really tricky and it's hard to see where things are canceling. So this is being multiplied, and I'm even going to write it as 20 over 1. And then this is minus 5 over 2 times 20 over 1, all over 3 over 2 times 20 over 1, minus 5 over 4 times 20 over 1. Okay, so if I chose an acceptable value, what will happen is I will no longer have denominators. I should have every single diagonal have some sort of a reducing happen with the denominator that's already there. So this 5 and this 20 both divide by 5, giving me a 4. This 2 and this 20 both divide by 2, giving me a 10. 2 and 20 dividing by 2 to give me 10. And 4 and 20 dividing by 4 to give me 5. Every single one of them reduces. If I still have a small denominator left at this point, it means that I probably didn't choose the least common denominator. I may have forgotten a factor somewhere along the way. Okay, so all of this now reduces or simplifies to actually multiplying the pieces together. So I have 6 times 4, that's 24. And I have a subtraction sign, and then I have 5 times 10, which is 50, so minus 50, over 3 times 10, which is 30, a subtraction sign, and then 5 times 5, which is 25. Okay, is everybody good with that? All the pieces, see where they came from and everything. Fabulous. All right, what is 24 minus 50? It is. Good job. Negative 26. 30 minus 25? 5. 26 and 5 don't have any factors in common. I know it's top heavy. That's okay. There's nothing wrong with that. We've talked about that before, but just as a reminder. So this is negative 26 over 5. All simplified down.
I didn't hear you got 20. I know the least common denominator. So what did you do?
I looked at the 3 numbers that are already my denominators, the 5, the 2, and the 4. And I recognized I could multiply them all together and get 40, and that would be okay. So you could use 40. It would not be a problem. Your numbers would just be a little bit bigger. However, I know that I really don't need the 2 as a factor considered because the 4 already has a 2 in it. So I don't really need the extra 2 when I'm considering it. So 5 times 4, because 5 and 4 don't have anything in common, being 20 is sufficient. It's enough, and I could use 20. But if you used 40, it'd be okay. Okay? All right, so all the problems we've done so far, all 4 of those, have all had just numbers in them, right? So it's kind of like the things that we were doing back in sections 1-4, 1-5, where we were just dealing with fractions on their own, right? Just on their own. And so we didn't have to deal with any variables, anything like that. But working with variables in this type of problem works much the same way. So now we're going to do some problems that have variables in them. So you'll notice number 5 and number 6 are actually a lot like problems number 1 and number 2. I know there's variables in them, but I have a single fraction on the top and I have a single fraction on the bottom, right? So I have a fraction divided by a fraction, just like I had on problems 1 and 2. So when I have a fraction divided by a fraction, I can simply multiply by the reciprocal. So the numerator stays the same, x plus 4 over x minus 5. And then instead of dividing by x plus 4 over 5x to the 4th, I multiply by the reciprocal, x to the 4th, 5x to the 4th, divided by x plus 4. Multiplying by the reciprocal. And then again, I'm looking along diagonals to see if I can reduce anything, and sure enough, there's an x plus 4 here and here, right, on that diagonal. The other one has a 5 in it and an x in it, but there's a separation with subtraction down here, so those are terms, not factors. I can only cancel factors. So I don't have the ability to actually reduce anything else. So I have 5x to the fourth over x minus 5. Okay, again, number 6, much the same. I have a fraction inside of a fraction. So the process works much the same. We will multiply it by the reciprocal. So you're going to leave the 8 over 5x as is. And we'll multiply by the reciprocal of the denominator. So it's 2x minus 10 over 2. So now I have 2 over 2x minus 10. Now, the difference on this problem compared to the last problem is that I have something, one denominator specifically, one piece, that's actually factorable. The 2x minus 10 is not in factored form. Right? I can reduce that. I can simplify the way that that looks. And I'll just do that in this same step by pulling out my 2. And so I have 2 times x minus 5. I'm just breaking it apart into its factors. And the reason I'm doing that is because I want to be able to cancel factors that are in common. In particular, I actually can cancel the 2 here and the 2 here. You also could have canceled the 2 on the bottom with the 8 over here and make this 4. It's the same thing. It's just canceling with a different piece that it cancels with. You can't do it with both. You got to pick one. All right, I'm going to go with the first one I saw, which was this one. And then if I multiply across the top, I have an 8. And if I multiply across the bottom, I'm inclined to leave them again in factored form. There's a 5x, and there's an x minus 5. Do you want to multiply them out? You can. It doesn't hurt anything, but it also doesn't really help anything. This is as good as it gets without actually doing more work than you absolutely have to. And that's always nice. Okay. Now number 7 is still a fraction side of a fractions, right? Simple, like one simple, not simple, but one single fraction on top and one single fraction on bottom. So the process works the same. There's just a bit more reducing involved in this one, so I wanted to show you an example. So this is 7x minus 49 over the x. And then you're multiplying by the reciprocal here. So 4x minus 28 over x minus 2 becomes x minus 2 over 4x minus 28. So much like the last problem, I notice that I have some pieces that could be factored, but I have more than one piece. The first numerator, I can pull out a 7. So this would be 7 and then x minus 7. The second fraction, I can pull out, or I can factor the denominator and pull out a 4 to be 4 times x minus 7. All right, so somebody tell me something that you see cancels. I'm x minus 7. Anything else? Good guess. There's an x here that could potentially look like it cancels with this. The problem is that this piece has got subtraction in it, so it's 2 terms, not a factor. So that one won't cancel. I think that's it. Yeah. So, again, you can leave it in factored form. We can write this as 7 times x minus 2 on top. And then on bottom, I have a 4 and an x, so just have 4x on bottom. And again, don't go get carried away thinking I can cancel x's or cancel the 4 and the 2. Those are all terms. I can't do that, right? I've got to look at factored pieces, and I don't have any factored pieces that cancel here, so I'm stopped at this point. All right, so number 8. Number 8 is like problems 3 and 4. So over here, remind you since we haven't done it in a while, on 3 and 4, we had fractions inside of fractions, but I also have addition and subtraction, so I don't have a single fraction on top and a single fraction on bottom. That's just like what's happening on number 8. It's not a single fraction on top, a single fraction on bottom. So my best bet is to find and multiply by the least common denominator. But I have least common denominator, thank you, of W and W. They're the same. So what should I multiply by? W, you bet. I happen to have little denominators, if you will, that are exactly the same. So I'm going to multiply the top and the bottom by that value. Again, it has to distribute. So I'm going to write it out. If you don't need to see it written out, that's your call. But be very careful. This is 2 over W times W plus 7 times W over 3 times W plus 2 over W times W. So lovely things, right? This W, 2 over W times W, the W's cancel. The other one, the 2 over W times W, the W's cancel. They happen to be 2 over W. That's interesting, okay? And then we're just going to multiply what's left, simplify what's left, I meant to say. So this is just now 2 times 1, so this is 2, plus 7 times W, which is 7W, over 3 times W, which is 3W, plus 2 times 1, which is 2. Perfectly reasonable to leave it written this way. There's nothing I can factor out of every term. I can't even simplify within the numerator or the denominator any by even factoring those pieces individually. There's nothing else that can be done, and I would be stopped at that point. Any questions on that one? Let's say for an instance that we had a problem. Let me just throw it out there just in case something should come up, where it looked much like that one. It had a 7 over W and it had a 3, but I had an 8 plus 6 over W minus 1 or something like this, right? So if those denominators don't match, which they don't now, I would be back to doing the same thing I did on those other problems, where I need to multiply by the least common denominator of both. So the least common denominator of W and W minus 1 would actually be W times W minus 1. And I'd have to multiply, in essence, by both denominators because they don't have any factors in common. So that's an option as well of something that could happen. It just didn't happen in the example that I used. For fun, let's actually finish the problem out so you have it as a reference point if it should come up. I can't remember if it does or not. So we're going to multiply by W and W minus 1 on top and on bottom. So again, it's going to distribute. So I have 7 over W times W and times W minus 1. And I have 3 times W and W minus 1. I'll make that a little bit smaller. It's running off my screen. There, just shift it over. And then in the denominator, we have 8 times W and W minus 1. And we have 6 over W minus 1 times W and W minus 1. So it looks messier. I do have some pieces that are not quite as friendly, but I still have the denominators, the little denominators canceling. That W cancels. This W minus 1 cancels. And there are no more little denominators to be had. What I do have now, though, is I have to multiply the 7 through here. So that's 7W minus 7. And this is 3W, and I can distribute it through here as well. 3W times W is actually 3W squared. And then 3W minus 1 is negative 3W. Denominator is much like that. I have 8W to distribute through. So 8W times W is 8, whoops, didn't mean to change that color. 8W squared. 8W times negative 1 would be negative 8W. And then here I have remaining a 6 and a W, so I just have 6W. There's not a lot that can combine, but there are a couple things that can. I have a 7W and a negative 3W here. So 7W and negative 3W would be 4W minus 7 plus 3W squared. In the denominator, I have an 8W squared. But then I also have a negative 8W and a positive 6W, so I have a negative 2W. It might help, just for the sake of argument, to rewrite the top so that the order of exponents goes downhill, right? It's descending. So negative 3W squared plus 4W minus 7 over 8W squared minus 2W. At this point, it would be useful to factor. I'm going to start by factoring the denominator, because once I do, it will show you that I don't need to factor the numerator. Denominator actually has a 2W in both pieces, right? I can pull out 2W. What's 8W squared divided by 2W? 4W, And what is 2W divided by 2W? 1. So the only way that this is going to reduce is if I can pull a 2W out of the entire numerator, which I can't, right? Or if I can rewrite these factors in the numerator so that I get a factor that matches 4W minus 1. But I can't, because the two numbers that they begin with have to start with 3 and 1. So I'm not going to get a 4 at the beginning of any of that, potentially. Like, that doesn't work. So there's not going to be any ability to factor this and reduce it, which means I don't necessarily really need to factor it at all. You could write it in factored form if you wished, but it wouldn't actually help you. Again, it's more work than is necessary because it doesn't reduce. You do need to make sure it doesn't reduce visually to check that. And then I'd be stopped at this point. It's messy looking at the end, but it's still as simple as it gets. All right, so we have homework 20 for this evening. I don't think there's very many problems. Let me double check on that. Oh, 15. So if you guys will get started, we'll end a little bit early today, but I think you might actually finish in class and then you won't have any homework over the weekend, and boy, would that be nice, right? Absolutely. So go ahead and get started, and we will continue on until about 10:30.